Thank you so much, Giuseppe, and again, you'll be on the panel in just a few moments. Next up, I'm very happy to welcome somebody who is right next to me for once. Carlos, you are a well-known figure in the Luxembourg scene and to many in the space industry as well. So the floor is yours. Carlos Espejel, who is Space Resources Utilization Lead at iSpace Europe. Carlos.
Thank you, Lisa. Thanks a lot for your kind introduction, and good afternoon, everyone. And I just hope that everyone is doing absolutely great anywhere in the world that you may be. I'm just gonna try my slides. Just gonna go back. Perfect. Yeah, as Lisa kindly mentioned, I am Carlos Espejel. I am the lead for the Space Resource Utilization Group in iSpace, and I will be very happy to share with you today about some of the iSpace activities that we have around data gathering, data acquisition, processing, and analysis, and how we're intending to report this data in terms of space resources. So as maybe some of you might be aware, in iSpace we have three main areas, which is lunar transportation with our lunar landers and our lunar rovers. At the same time, we're constantly looking at forming technological and business partnerships, of course. And the topic of today, of course, is lunar data, where we can acquire data, process data, sell data, not only for resources, but for any industry that is planning to go into the future moon ecosystem. So in terms of lunar data acquisition, as I was mentioning, we got landers and rovers, not only to collect resources data, but environmental data, R&D, scientific, media. But because of the topic of today, resources, we actually do have capability to cover large areas, maybe at lower resolution. This is with our lander, where we can do orbital work with remote sensing, and of course, the instrument will depend on the customer. At the same time, we got capability in terms of covering smaller areas, but to get higher resolution in terms of geological resolution, for instance, with our rovers. Not only remote sensing, but at the same time, ground truth. Ground truth on the surface, and ground truth in situ. So below the surface, again, as for elemental distribution, with technologies as drills, for instance. Now, at the end, it's going to be a trade-off between the area coverage and the resolution. And of course, this will depend on what the customer needs and wants to report, of course. Now, in terms of reporting, we will be following mining and oil and gas best practices. For instance, we are looking at reporting our exploration results to industry standards like LORS, JORC, and I'm going to speak a bit more about this. So once we collect this data from lunar data, we also have the capability of processing this data and do further analysis. For instance, once we have this lunar data, we can do some mission planning, again, resource-related as landing zones, prospecting and exploration campaigns. At the same time, we can do some geological modeling following mining industry standards, not only for science, but for resources, as you can see on the screen. And we can do some resource estimation, and I will show you an actual example of a resource estimation activity that we run. And because now we can actually model and estimate some quantity, quality, and distribution, structural resources, not only on the surface, but subsurface. And I will share with you just a bit later. Now, in terms of resource estimation, we can also now estimate, with the data that we have, of course, how much of these resources are actually economically, technically, and technologically extractable, again, with the data that we have. And, of course, looking then at the optimum sequence of extraction. And one of the most important things is what is the actual economic value of these deposits. At the same time, in order to estimate reserves, we need to model and optimize the SRU value chain. And in terms of one of the important steps of value chain optimization is estimating the optimum capacities and productivities for extraction, beneficiation, refining, and selecting the optimum method of extraction and processing. And this is within value chain optimization. We would like to show off that we also have mission planning toolkits that they are web-based, where we can do our own geo-referencing and do calculations for horizon, sun, and air visibility that we do in-house, of course. Now, as I was mentioning, in iSpace, we have the intention of following best practices, as in the mining and oil and gas industry. What do I mean by this? So, for instance, in the mining industry, when they want to report exploration results, resources, and reserves to the stock exchanges, they need to follow standards. Therefore, investors, they only invest in companies that are compliant and projects that are compliant to these standards. So in a similar way, in iSpace, we're looking at reporting or exploration results, resources, and reserves following standards for space resources for the sake of our investors. Now, of course, the question is, what are the standards for space resources? And this is where LORS 101 comes into the game. Now, but let's start with the existing standards that exist on Earth. So, for instance, for the mining industry, we got JORC, which is based in Australia, the NI 43101 based in Canada, and CRISCO, which tries to put all the standards of mining together. So if you're a mining company and you're trying to report your exploration results in the stock exchange, you need to use one of these standards. In a similar way, if you're an oil and gas company and you're trying to report your reserves to the stock exchange, you need to follow the PRMS standards for oil and gas. There are also some standards for, from the United Nations. Now, why do the mining and oil and gas industry need different standards? And this is because their geological deposits are different, and because the technology and methodologies for extraction, processing, and refining, they're completely different. And of course, their markets are different. So in a similar way, for space resources, most probable, the geological deposits will be different, and for sure, the extraction, processing, and refining technologies and methodologies, they will be possibly completely different, and therefore the markets as well. So because of this, we need our own built-for-purpose standards for space resources. And this is where the project LORS 101 started in 2018, the Lunar Ore Reserve Standard, which is a Luxembourg initiative through the FNR, the University of Luxembourg, iSpace, ESA, and UNSW. Just to share a bit more of the objectives, so LORS is designed to provide the first framework and guidelines for private companies, space agencies, and any entity that would like to explore and use space resources, not only the moon, but planets and asteroids. And this is very important, in a clear and responsible manner for scientific and commercial purposes, so for sales and non-sales. So LORS contains 4 areas. First, it has 3 classification frameworks, which I will share with you. It also has a glossary of definitions. For instance, what is the difference between resources and reserves? And compliance. And here it will make, of course, reference to the work that is happening with The Hague, with Artemis, and the work that we have been listening in the last presentations. At the same time, the guidelines for transparent reporting. So something I would like to point out here is that LORS is an independent, inclusive, collaborative, and living document or project. So with this, I would like to open again the invitation to anyone that would like to be part of this to please reach us out. So with this, as I mentioned, there are 3 classification systems. And just really quick, the first classification system is for geological survey missions, for instance, L-CROSS, which their purpose was to do a survey mission on H2O. Then CS2 is for operational non-sale purposes. For instance, NASA, that is planning to extract H2O for operational purposes, but not sales, so that's CS2. And then it's GTECS3, which is for commercial and sale purposes. So in this instance, iSpace ourselves, which we're looking at extracting H2O and selling it for commercial purposes, we would use CS3. So just to give you the details on the first classification system, CS1, this one is for geological survey purposes. So it measures geological certainty. So how do we increase geological certainty? This is through activities as exploration. For instance, within exploration, you have prospecting. And prospecting covers large areas, remote sensing, orbital work, and lower resolution. Then you have ground truth exploration, which is smaller areas, higher resolution as for rovers. Then you have sub-activities as surface exploration targets, where you get samples from the surface, and in-situ exploration targets, where you get in-situ samples, for instance. Now, with a combination of activities and sub-activities, you can then raise your classification system, your geological certainty, from speculative resources all the way to measured resources, which is the highest hierarchy. Now, there's another concept called the geological discovery test line. So pretty much, if you have not done any ground truth exploration, it is considered undiscovered resources. But if you already did some ground truth exploration, it is considered discovered resources. There are other classification systems, but the last one that I want to show you is that you can only call reserves anything that has high geological certainty and that is economically, technically, and technologically extractable. So with this, I just want to finish with one example of a real resource evaluation example. So with this, we actually grabbed high-resolution DTM data, the thermal models of potential permafrost, and hydrogen anomalies, and we created, following mining industry standards, a block model, a 3D block model where now you can actually see the distribution of potential permafrost on the surface. Now, what is the beauty of this? That now we can start estimating the tonnages and start planning some potential extraction and even processing landing zones and so on. And not only for the surface, but this is showing a cross-section where you can see the potential permafrost at 1.5 meters in depth. Therefore, you can start planning how much extraction of overburden or waste or regolith you need to do before reaching the permafrost. And if we have to report this under LORS, then we would say we use the classification S1. The main activities was exploration and prospecting using remote sensing. The sub-activities were surface exploration targets, and the resource classification, this is prospective resources because the geological knowledge error is plus minus 75. And it is pretty much undiscovered resources because the JKE is above 70%. And for us in iSpace, therefore, after doing all this analysis, our next step is ground through the exploration, through rovers, to get a classification level of inferred resources. So this is just showing you a real example of resource evaluation and how would we be using standards for reporting. Thank you.
Thank you so much indeed, Carlos. You're speaking so fast, my brain is trying to take it in the same pace as your brain is working.